welcome back to BCodeTube. If you like this content, subscribe to the channel, leave a like on the video. So far, we have seen a couple libraries that can replace NumPy in C++. They are basically linear algebra libraries. So far, we have seen Eigen, we have seen numcpp, we have seen xtensor. But can we use NumPy itself in C or C++? Well, yes, I'm making this video to show you how to configure your project to use NumPy directly in C or C++. So if you have followed previous videos, you see that I changed a little bit the structure of the project. Basically in libs, I have here the parser that parses the raw data. And these are the neural nets. Each one is using a different library. This is the one that uses Eigen, and this uses Blaze. It's a different library. This uses numcpp. This uses openblas. This one uses xtensor, and yeah, Blaze. And we are gonna see here the NumPy one. And the examples is all the main files. So this is where we have the main that calls the libraries. So also one for each library, and also the torch examples, right? And let's see the NumPy. So to do the NumPy, we need to first find the virtual environment that I have created here. Well, if you don't have the virtual environment, it will use your system's setup. Let me show you what I mean by this. If I open here Python, import numpy snp np.version. So this is where it is installed in my system. So here is where I have the apt search python 3 numpy. So this is what is installed in my system. But if I open here a new one and I activate the virtual environment, activate. So now it's active here. So if I open Python, import numpy snp np.version, you see that it's a different version from what we had here. If I configure cmake as is right now, it will find the virtual environment here and the executable and the site locations. This site is where we have the installed libraries for the virtual environment. If I remove here, for example, you refresh the cache, you see that it doesn't find the virtual environment. It only finds the system, the installation, even though I have this set. I don't know if this works at all, but well, reset the cache is basically delete this file here. So we want the one from the virtual environment. If you use this is Cilion, but if you use PyCharm and you have configured the interpreter, for example, let me set here. Even though I commented here, it will find the location because I have configured in the environment for the tool here, my IDE. I don't want this to be set now. Let me remove this. Yeah, so now it's the system, but I don't want the system. I want the virtual environment. So let me see if I can just reconfigure. Yeah, so now it is configured virtual environment. It found the components that I set here to make sure that NumPy is installed, and that this is the correct version. So I passed to the C file, C++ file, these definitions, the locations of each one, because we're gonna use it in the code. Because even though CMake finds it, when you run, it still load dynamically. So the final executable still needs to find the location of the libraries. Oh, it's missing here the site, the standard lib. We still need the standard lib because even though I installed the NumPy here, NumPy uses some of the standard libs to execute. So then we also are gonna need the standard lib location, right? So these are the compile definitions. And then to link the libraries, you do the namespace Python, and then this is the interpreter, this is to load the modules, and this is the NumPy. And then by doing this, CMake will find the correct location, which is here, include. These are the headers, and the libraries is here. If we take a look here at the build for the project, this is the project, you see that in the includes, it correctly detect the location of the headers for the NumPy. Okay, and now in the code, what we do is so the structure of the project here is I have set up here a class for the NumPy. This I will explain later in the array. For the NumPy, I do not allow the creation of objects for class NumPy. I use the singleton design and the single pattern design, and I create the instance, but the instance is in here, not this py handle. So I create the instance in the cpp file, a global named space variable, and so that our binary here, where is the binary here? It will only call static methods. So all of these are static methods to simulate the, like when we do in Python, like np.random. Then the idea is that here we are gonna do c numpy random seed, right? Where do we have here np in Python? The code is in the class. So here np random rand So what we are gonna do here is in the class for the neural net, we do here NumPy and RNG random. But how do we get here, right? We go to the constructor, and in the constructor, I check if the root has been set from here, from the definition. And if so, we have to define this this config inside this object config. We have to define this and set the paths accordingly. Pay attention that I use this to get a wide chart. And not only the standard lib, but I manually have to set here. It's where dynamic libraries are located for Python. This is necessary for runtime. In the runtime, Python is gonna look on these locations to load the libraries. If you don't set this, it's not gonna find the libraries. If you don't set the root dir, or if it can't find the environment, then it will just initialize Python as is, no configuration. It's gonna be passed through. Okay. Then here I use this function. It is a Python function to import the module. And if it doesn't find it, throw an error. So this comes from Python itself, and this variable is a PyObject. All the members are PyObject in this class, in the class NumPy. And this is also, it's a helper function that basically calls this import array. This is necessary for NumPy to load the array module inside of it. And go back, and then I load each one of the internal modules here in the from NumPy. So this, let me just put on the side. This is when we do NP array. Probably is in the neural net. Let me put it here. So when we do when we do NP ND array, so this ND array is this one, and we check if it's a callable. So we get the string. This is to get the pointer inside the library, and with the pointer we check if it's a callable object, all from the Python C API. The same thing for random. Random is used here in the random. So every time we do np random, it's numpy.random, and I save in this object, and I do the same for the others. The for RNG is to get the generator, RNG generator, the random numbers generator. And inside the random number generator, I try to find the random function. This is the method for the generator. The zeros, also I use here zeros. So np zeros, then find the zeros. Add is the function add. Basically is when we do the sum, or here, no, not here, here. When we do this sum, we basically, Python is calling this add function. the max we do here, the max subtract is when we do the subtraction of two arrays, NAD arrays. The dot is here, the dot product, maximum, and exponential. These are all the same functions that I have here. np dot something, sum, exponential is used here. Divide is when we do the division here. So Python calls the function for us. Argmax, we use argmax here. Equal is when we try to get if two arrays are equal. Greater is for this to know if it's greater than 0, to do the relu part. And transpose is when we do the dot t, is a transpose. And reshape, we use reshape at some point here. Here reshape. Yeah, these are all the what we need from the module, from the NumPy module. We need to load them, and I load them as members in the class. And if you know the Python C API, we know that we need to unload them in the constructor. So I call the finalize. I do the x decrement because if it's not loaded, if we just do the decremented and it's already 0, the counter, then it will fail. So the x is true. If it's 0, ignores. But I make sure that the main one is actually unloaded, and then I do the Python finalize. This is to close the Python interpreter. I think I can close this now. No, then for NumPy, I call the functions. Basically, what I'm doing is I'm getting the pointer that I loaded before, and I pass the parameters and call the function, and this function returns an array, and it's a array object, but then I pass it to my own class that I'm gonna show in a few moments. So basically all the functions are like this. I call the pointer and I pass the parameters. Here, for example, to get the argmax, I need a parameter to pass to the function. Let me open here the Python. It's here. No. So argmax, I need to pass here this parameter. This is the what, if it's a row or columns, right? And then I need to create an Py object from this, from the primitive. So this is a primitive, a long, but I need to create a Py object from long, and then this parameter I pass to the call object. So I pass the object and the argument. And what is this C and D array? So C and D array, right? It's a class that I created here, and the idea of the class is just to hold the Py object, and in the destructor it will clear the reference. If you know the Python C API, every time you create a Py object, before you destroy it, you need to decrease the. This is gonna destroy it, right? You just hold the reference for the pointer for the object, but and then Python increases the counter. So when it's time for us to remove the object, then we have to decrease. So this is basically what I'm doing is what they say is RAII. So when when the result, I convert it to, I pass the object to this CND array so that when this is not needed anymore, then it will auto decrement the counter for me. So I don't forget to decrement the object. And this class, I overload these operators, so then it's easy for me. I can create, for example, CND. I can create a CND array A. I can create a B, and then I can, for example, do just auto C equals A plus B. A plus B, because I have the operator here to. I don't have. I can do the minus then. So with the operator minus and this operator overload, I can simply do this in C++. We cannot do this in C. C doesn't have these operators overloads, but C++ we do. But then, why do I need those in the NumPy class? It's because basically what I'm doing here is I'm calling the static member from the NumPy, and I pass these guys as parameters. So the class overloads the array class overloads the operator, but then it calls the NumPy class, and then the NumPy class calls the pointer that we loaded in the beginning. So if we see the neural net here, the neural net backpropagation, for example, this is and the array member of the neural net, and I just do this. This is the overload operator from the target, and this is the also another overload for the array. And then if we look at the neural net here, the Python backpropagation, it becomes almost the same code. So this is the one hot, it's my target. So subtract here, and then we do this division by size. I do the division here, but it's basically this 1 dash m is this, it's like a 1 dash m. Epsilon size is the m. And then here, to get the transpose, I just call the transpose function. The transpose function is also just a redirection to the NumPy. And yeah, it's almost the same thing here. Besides, for example, I don't have the shape, so I just call rows and cols. But the rest here, the dot, I do transpose, and then I do the dot, and I pass the other array. And here, this is the same thing, right? Just swap the order here, but the algorithm is the same, and the visualization just to read the code, oh, this is I'm subtracting the derivative multiplied by the alpha. That's the same thing. I'm subtracting the derivative by the alpha. And let me just show all the functions one by one here in the class. So I initialize here with random values. I'm initializing here, but we don't need, because it is a member of the class, even though it's self here. So these are members of the class. And the relu, let's see, the relu here is relu. Yeah, it's the maximum. Then the next one, softmax. Here, softmax exponential of z. Okay, so I found here an error, but I quickly fix here. Basically, I was missing the subtraction with the max for x is 0, and I had to create this function here quickly. And it's good that I can show this is also another class to hold the object. So if we are just receiving the object, it just stores in the class member here. This class is a small class. Let me get the, yeah, it's defined only here in the CPP. Is not defined in the, it's not declared in the header, because I'm using only internally here. Users are not supposed to call the Python API, the idea of this library. So it's created only in the CPP. So only this CPP file will have reference for this Py handle. And when we receive, we just store in the object. It's the only member that we have here. And this is the copy assignment. So when we are copying the object, then we have to increment the counter. This is the move. So in the move, we just copy the reference of the other, and then the other becomes null. So then when Python do the decrement, it will decrement null pointer. It's not, it checks for null pointer, so it's not gonna do anything, right? And this is the copy assignment. So we have to decrement ourselves, copy the reference, and then increment the other, because we are the other might already have something, so we are just incrementing what the other has. And this is the move assignment. So we decrement ourselves if it exists. It checks for null, as I said. So we copy the other, and we just set the other to null. So then when the other goes out of scope, it's not gonna decrement. And then when ourselves go out of scope, then we decrement the reference that we have. And this is to get the object. Yeah, so then this in the softmax we can use as the parameter, where is the max function, right? We can use as parameter. And so when this function returns, this object gets called the deconstructor, and the deconstructor releases the reference. So then by doing this is a way for me to not forget to decrement the object. The class is gonna do the decrement for me. And yeah, it's used for any Py object. This is a long from long, and this is a float from double. And I think I have other. There is one that's a tuple. I don't know if I'm gonna find it here. From long. I think I can just check here from double here. So basically here I'm creating a tuple. This is how many values this tuple has. So 2 values. One is a long and the other is a long that I receive here. And then it's the shape parameter. So then I can use this shape as a call to the reshape function. So as we saw before, it's row and columns. So I pass here the row and columns as a shape tuple, right? And then we call the function and return as the array. Yeah, let me then just continue here. I fix this softmax and the sum, the axis, and then I return the division as a the array. The forward propagation, yeah, it's a dot, then we sum with the b1, then a ReLU, then another dot, then sum with b2, and we call the softmax. One hot, let's see, we create a 0 array, and here is I had to do the loop. So this a range is basically going to create a range from 0 to the size of y. In my case, it's 5,000 samples. So it's going to be from 0 to 4999. And then get the y value in that row. And that set the value to 1. This is the one hot. Here, we don't have the same function, but because I'm only using this kind of indexing, so what I'm just doing is I'm looping through all the zeros. Z, as we're gonna see, it's the y values. So for all the rows, for each row, I know that is only one column. That's why I put 0 here. So for each row, that's the range. All of this 0 to the row size is all of this a range. And then I get the value of that row in that in the column 0, that I know that it's only one column. Y has only one column. And then this index, this value becomes the index on the output, and the one hot, and the output is transposed like here. The ReLU is just to see if it's greater than 0, and we do this by overloading the operator. And the break propagation, it's here. We saw that before, so we do the subtraction. This is used in all the matrix, so I'm just calculating here, and then I do the sum on the axis one. I reshape based on rows and columns, the shape here. I transpose dot derivative for ReLU, and then here, for example, if I need to do the NP sum, I call the NumPy sum. Yeah, and then we do the alphas here, the derivative. The predictions is the argmax. Yeah, the argmax here. The sum is if they are equal, then we sum how many are equal. That's what the neural network corrected, predicted. We compare with the predictions with the y, and we sum to get the total. and the accuracy is this simple, this primitive calculation. Okay, yeah, that's how I set up the neural network and the NumPy, basically overloading the array operator and then calling the NumPy, and the NumPy calls the pointer um, in the module that we loaded. Um, let me look again the loader. The loader is private, so users are not gonna load this. And then let me show the main file. Basically, the main file here, we create an array with these dimensions, and then we set the values index like this. We get the values and we set the values the same way. All right. These are not related. And then here to get the index 4, here we don't have the shape, but we do have transpose. We get the max, and then these are neural network stuff to get the. So yeah, you have to see the videos before to understand this. The idea here is just to show how to get the environment set up, and how to find numpy.ndarray or numpy.zeros. That's the idea of this video. Just show how to set up the numpy into your C++ project. The actual neural network, you have to watch the previous videos. Okay. Yeah, and just to test here, I compiled the. Let me do a clean compilation. Okay, so I finished recompiling everything here. Then I did some testings, and this is with the Eigen library. We can see that 2.9 seconds. This was the fastest one. Then we had the Torch with 2.3 seconds. Then we had the NumPy with 2.8. Then we had openblas with 3.1. Then we had the Blaze library with 4.6. Then we had the numcpp, which is 17 seconds. And the worst case was xtensor, 55 seconds. Maybe my setup for xtensor is not that correct with the SIMD instructions. I will check this later, but this was the worst performance compared with all the others. And yeah, Eigen was the fastest one, although there is a learning curve to learn if you want to know Eigen. Let me open here quickly just to show you. Yeah, this row-wise stuff is, when was my first time doing this, I had to put my head to think about it a little bit, and but yeah, what CY's product was one that I had to figure out. Otherwise, they also have like transpose and zero and sum. So once you get the hang of it, it's fine. This unary, like you have to apply function here. So yeah, because it doesn't have equal to compare, right? So you have to check if it's below a threshold to compare data, float values, right? Yeah, Eigen is the fastest one with a little bit of learning curve. Torch, then it's also you need to read the documentation and learn the library. Yeah, it uses torch functions itself. So when we do the predictions, yeah, it has its own like back propagation. The loss functions, these all from the torch library itself. I did not program this. The optimizer, and you do the backward and then do the step. So torch has its own methodology, right? And then on openblas, I did not make a video on openblas because it's kind of complex the way it is, because you need yeah, let me show here the. So you need to always done with free functions. This is pure C. openblas can work with pure C functions. So it's all this to do the multiplication. You have these free functions, the exponential of each value. Oh no, this I did. This you did a for loop and then the exponential of each value individually. So this is to sum two arrays. Basically, you do the alpha as one, and then you can sum the alpha vector to a matrix. So it's quite complicated, and yeah, if you want a full video on openblas, I can do it, but I don't have the intention right now to do this. Then Blaze, let's see Blaze a little bit. Yeah, well, we can close this. Blaze is a C++ library and also has the same functions like transpose and sum, but you see that they use name differently. You can do like it has overloaded. You can like do this division. It's from their own library. They overloaded, so that's easy to do the calculation, but it's not exactly the same. So you do need to read the documentation a little bit to understand. But some things are the same: argmax, sum, exponential. But yeah, when dealing with indexing here, the transpose is like this. So yeah, a little bit different, but we can understand, right? It's almost the same. And yeah, the NumPy surprised me because I thought that these Python objects would be on the way of the calculations, but they seem quick enough. Not the pointers, right? These Py objects, because we have to increase and decrease the counters, the reference counters. So here, when we create them in a loop, I thought this would be on the way. Now they see this only once here, the max. Yeah, but it seems very quick compared to the others. And well, once the setup is done, the setup is the difficult part, because you need to do the environment correctly. If not, it will get the system, and if you get the system, it will get the wrong version. I closed the NumPy here, but Python import NumPy as np dot version. So yeah, the same here. I need to venv binary activate, and then Python import NumPy as p version. So if you don't do it correctly, you load another version that maybe it's not very well optimized or doesn't have the function that you need, and you need to do all of this get string and check if it's a callable. This is it's a module inside NumPy, so a module inside a module, but then from there you can get the sub functions, and then yeah, you have to deal with increment and decrement of reference, you're creating tuples to pass a shape. So if you can copy this class. It doesn't have everything. Probably if you need something else here, I do the subtraction with a double, but I don't have subtraction with a long, for example. So if you need that, you have to expand this, but at least the most difficult part is done. Would be just a copy and change a little bit. But the performance, I think it's worth to do it compared to Eigen, because also Eigen you need to deal with C++ packaging system, which is not very good, while with NumPy I can just come here and do an update on the pip install update, pip update NumPy, and then I already get all the new functions, all the new performance, if there is any. So I think it's nice to work with NumPy in C or C++. In C, you will not have the namespace in the classes and the auto increment and decrement. You would have to decrement and increment yourself the objects, but it's not that difficult once you understand what you're doing. And right, just remember at the end of the function here, this long here, the seed, at the end of the function it gets destroyed, so you have to do it yourself, but the increment and decrement, but if you think you can do it, you can do it in C. I prefer C++ exactly because of this. I can just do the decrement here and forget about it. And yeah, non-CPP, non-CPP, this one, it's good, but yeah, it has a long way to go in optimizations. I think underneath it uses the standard STL, the templates, but yeah, I would prefer to just use NumPy with this setup that I already have, and you can check in the Git. In the Git, I have all the project there with the CMake and all these classes that you can copy. And yeah, I think that's it. If you like it, leave a like on the video and let me know what you wanna see next.